So we are live now. So, folks, before I move on to do yet another review problem from section 3.7, and that's going to be the last one. I said earlier that this is essentially the last section of chapter 3, and the reason for that, for saying that, is because the next lesson we're going to skip 3.8, so we're not going to cover Newton's method here. We're going to move on to 3.9, which is a section about antiderivatives. And the section about antiderivatives, folks, is going to be dealt with in a totally different fashion. So we're still using the notion of derivatives, but we're using it in a totally different way. So we're really starting the new chapter, if you want. This section could have very well been 3.9. I'm referring to could have very well been the first lesson of chapter 4. All right. So that being said, let's get started here. And again, if you have any questions, do let me know, folks. Check the speed of the connection. I didn't realize sometimes it's getting slow. I watched some of the recordings. But there's nothing I can do about that. So do let me know if you don't hear or if it gets interrupted, the connection, like it happened last time. I may not be aware, so don't let me speak here without any interruption. So it's better to interrupt me and let me know. All right, folks. So today we're gonna continue and we're gonna do a lesson. So we're gonna do problem 13 from lesson 3.7. This is on optimization problems. So this lesson, all the problems here are supposedly of very practical, with a very practical flavor. But again, as I said, not all of them do really meet that criterion. So some of these are just artificial problems. Anyway, chapter second lesson, so problem 13 looks more like a problem that's anchored in reality. So that's the reason why I'm doing that. A farmer wants to fence an area of 1.5 million square feet. So the area that the farmer wants to fence is 1.5 million. Now, instead of writing 1.5 million like that, let me write 1.5 million like this. Let's do here. So let's write 1.5 million is 1,500,000. So it's square feet, so we can say here feet square. All right, so this is what the farmer wants to enclose. And it says it's a rectangular area in the problem, so it looks something like this. And it says to divide it in half with a fence parallel to one of the sides of the rectangle. So our farmer divides the whatever yard here in two parts. So one part, let's say here where he places chicken, and another part, let's say here where he places some other things, rabbits or some other things. So this is what the farmer does, and then he says so he has the area, this area that's prescribed somehow, in practice, and he needs to minimize the cost of the fence. So minimize the cost of the fence. Now what they tell us in the they don't clearly tell us in the problem is that Is that the fence that that this farmer so folks, the fence that the farmer uses over here, so would be the sides obviously, and this one here, the one that's in the middle, will be priced linearly proportional with the cost. In other words, he goes to, I don't know, to Menards or Home Depot or wherever he finds fence, and he buys the fence at X, $5 per linear yard or something like that, or something. So that's kind of the idea here. So the cost of a fence is really proportional to the length that he uses here, and that in mathematical terms. So what he wants to minimize is, yes, the cost of the fence, but equivalently he wants to minimize the length of the fence. So by length meaning, and let's say perimeter. Well, maybe we should say perimeter here. So let's say perimeter, because length would be like going this way maybe. So just to avoid confusion, perimeter of fenced area, if you want. So this is what he wants to minimize. And now we have to set up a problem and solve it. And the way to set up a problem is, as usual, folks, you want to give names for the unknown quantities. So the unknown quantities are, in this case, would be the length, which I'm going to call it X here. It doesn't really matter which name you choose for it. And then it's going to be the width, which I can call Y over here. So what my farmer knows is that so the farmer knows that X times Y is 1,500,000, and he also wants to minimize, so the function that he looks after, the function to minimize is going to be the length of the perimeter of the enclosed area, which would be X over here, and another X from here, so that will be 2X. And then will be 3 Ys, because there's one here and there's one going down here and there's one going down here. So the vertical, the north-south sides of the fence. So 2X plus 3Y has to be the function to be minimized over here. So to minimize this particular function, he would need to, again, to make a function of one variable, folks. So just one variable, which basically boils down to, I'm sorry, I can't see what the camera is showing. So is that, let's see, it doesn't show much. Oh, okay. So I can see now. All right, folks. So the function to minimize is this one over here, and we need to express this in terms of just one of these variables. So the preferred variable would be, in this case, let's write the number X from here. Let's write it as 1,500,000 divided by Y, for example. So I can solve for X in terms of Y. And then I can write my function down here as 2 times, X, which is 1,500,000 divided by Y plus 3Y. And that is going to be, so if you add these together, so it's 3 million at the top, right, when you multiply by 2, divided by Y plus 3Y. So let's write it the other way. So 3Y plus 3 million divided by Y. So I'm not doing anything intelligent here. I'm just moving these around in the sum. So this is the function to minimize. I'm going to call this, let's call it f of Y. And to minimize this function, again, remember the usual way we do derivatives. So we're going to start, we're going to look for critical numbers, right? So we look for critical numbers of this function f, which means do f prime of y equals and calculate f prime, right? So that will be 3 because it's in y the derivative, so it'll be 3. And from this one here, so it's 3 million times y to the negative 1 if you want. So when you do a derivative, it's going to be plus 3 million times y to the negative 2, but y to the negative 1 was initially there, so that's going to be negative 1 times y to the negative 2. So if you take this function, I'm going to write the exact same function of the next page. So I'm going to say f prime of y equals, and what was that? We said 3, and I'm going to combine here, folks. I'm going to put the minus in front here. So I'm going to say, oops, wrong page. 3 minus 3 million, all right, times y to the negative 2, which could be written as 3 minus, 3 million over y squared. All right, so this is the one that I am going to set equal to 0, this derivative, because I want to find the critical number. And if I solve this equation here, it's not going to be terribly difficult. So I can say, let's move 3 to the other side. So we have negative 3 million over y squared equals negative 3. Divide out by negative 3 on both sides, and you'll get that 1 million. So let's put 1 million here, folks. Divided by y squared equals 1. And that is going to be the same as saying that y, if you solve for y here, just multiply by y squared would be 1 million. And you can take the square root of that, and you will see that y turns out to be simply 1,000. Now 1,000 what, folks? So remember that the area was measured in feet squared here. So when we take the square root, we end up with feet. So y will be 1,000 feet. That's going to be the answer to my problem. So this one here will be 1,000 feet. And if y is 1,000 feet, remember that x was calculated earlier in the problem is 1,500,000, etc. Divided by y, divide that. So it's going to be 1,500. So it's this is the situation for the area here. And that being said, we calculated something there, but how do we know that this is a minimum or a maximum? Because my function here was this one that you can see over here. So to know that this is a minimum, actually, so it turns out to be a minimum value, you can, for example, you can graph this particular function, and you can see that it does indeed have a minimum when the numbers are 1,000 and 1,500. Or you could simply take a look at the sign of a derivative, and the sign of the derivative being this one over here. So folks, for most practical purposes, it's just fine to finish here. So you just say that x is 1,500 and you're set. But if you want to be very rigorous, again, you can look. So this is where the problem could end. And if you finish the problem up to this point on the test, I'm just going to be just fine. However, if you want to go one step further and show me that this is truly the minimum and not the maximum, because it could be a maximum, we didn't rule that out. You can look at the sign of a derivative and you will easily see that the sign of a derivative being this one here, the derivative, or this one over here, you could easily see that, for example, when y is, so where did we get, oh, y 1000. Okay, so when y is less than 1000, for example, when y is 1, 3 minus 3 million divided by 1 is a negative number because it's 3 minus 3 million. So, so the sign of a derivative, if you want, you can put 0 over here. It doesn't make sense at 0 of a derivative, but it makes sense here at 1000 where it is 0. So f prime is that. We saw that at 1 is negative, so it's negative on this side, and we can actually check that when y is, for example, 3 million, 3 minus 3 million divided by 3 million squared, this is a very small number over here, certainly less than 3. So the derivative will have a positive sign here. You can check this with a calculator, but with decimals, but that would be a little unpleasant because the numbers are kind of large here, so you kind of have to zoom out a lot to see the values. Anyway, so that tells me that the function f is decreasing and then increasing like that, and this is indeed going to be a minimum, and that's going to be sufficient for our purposes here. So if that makes sense, folks, we can finish up our problem here. Again, I'm fine if you don't do this part. So this is a bit more sophisticated for math majors, the justification. If you end up with the numbers here, I'm just going to be just fine with that. All right. So that being said, we covered another problem of those optimization questions. Now, what's going to happen next? So I am going to give out just a couple of these practice problems from this section on the test, because again, there's a variety of applied questions, and some of them are tricky. But it's more like kind of getting used to a certain type of language versus really solving a practical problem. So these are some specific types of, if you want, practical problems, which again, it's a goal if you are maybe going to be an applied mathematician. But if you're not, most likely these types of problems, will not be the ones that you will ever see in practice, because most likely in practice, if you do physics, chemistry, biology, and some other things, you do maximize and minimize functions, but with different other constraints, and it's subject specific. So I'm not going to go into the details of that. And I am going to stop here with this particular lesson of optimization. All right. Again, if you find any, so look in the section, folks, and there's specific problems that obviously are, physics related problems. I see here a biology related problem with the vascular system, and so on and so forth. So depending on your major and your interest, let me know if you want me to go over any of these problems here. I could go very easily, and yeah. So let me know so we can actually discuss about that further. But myself, I'm not going to worry much about those, because again, for each subject, you would have to kind of spend some time to study those. And instead, I am going to move on to lesson 3.9. So we can consider, if you want, we can consider section chapter 3 finished. 3.9, I told you, is a completely different topic, or if you want, is a bridging topic between chapter 3 and chapter 4. So up to this point, folks, I'm going to write the title of 3.9 here. So it's called antiderivatives. All right, so chapter 3 and chapter 2 were chapters about derivatives. So everything we did there has something to do with a derivative of a function. Chapter 4, including 3.9, has a different flavor to it. It uses the concept of derivatives, but it uses in a specific way that leads to the notion of antiderivatives and integrals. So let me explain what the problem is here. Let's say we have a function f, and we calculate the derivative of f, and we find out that the derivative of f is g. So we can write that in words. The derivative of f is g. All right, we can write that in words. But equivalently, we can say the exact same thing as, and right now we're not going to use notation, although I could show you what notation is. So somehow this book wants us to kind of keep the mystery around notation for antiderivatives, and maybe it's for a good reason. I'll explain you what the reason is when we get there. So we can say the exact same thing by going the opposite way. So over here you can see you can start with f and say the derivative of f is g. But over here on the other side, you can say you can start with g and you can say the antiderivative of g is f. So this is the notion of antiderivative is simply, folks, is simply reading things from right to left. So the antiderivative of g is f. All right. Now that being said, today's lesson, the rest of the lesson, is to familiarize ourselves with writing things right to left. In other words, we take the derivative and then we say the antiderivative is that. So it's more or less a lesson where we psychologically get accustomed with the notion of antiderivative. So understand what the antiderivative is. So let me give you some examples. So for the remaining part of the lesson, we're going to do some examples. It's a short lesson in a way because we're gonna come and reinforce that tomorrow. So tomorrow is really the main bulk of the lesson. This is just an introduction, I think, and I think it's a good idea to just introduce the concept and let people digest it, and then come tomorrow and come the next day and finish up like complete, show some formulas and things like that. So today we're not going to show any formula, folks. So I'm going to say here, here's an example. The derivative of x squared is equal to 2x. Let's write this as an antiderivative. So to write this as an antiderivative, we're going to start from here with this guy, right? So we're going to say the antiderivative of 2x is x squared. The antiderivative of 2x is x squared. And that is the way to read this thing over here. So antiderivative of what we have on the right side equals, the one we started from the left side. All right, another example. Let's say x to the negative 1 primed equals, and be careful here, so this is going to be equal to negative x to the negative 2. And to read this with antiderivative, we're going to say the antiderivative of negative x to the negative 2 is x to the negative 1. So it's the function whose derivative is negative x to the negative 2, which is what we wrote there. So that is the way to write this with antiderivatives. And I think at this point in time, you realize that we're going to do a bunch of other things that look very much like this one here. So to prepare the ground for tomorrow's lesson, I'm going to list a number of derivatives here, and we're going to draw some observations, and then tomorrow is again, we're going to derive some formulas. Now, if this were a face-to-face lesson, I would probably say, at this point in time, let's do some group work and stuff, and there we go. Here's some derivatives, and please work on those and such. But because of limitations of technology, you don't have a tablet like I do here, and it's kind of hard to communicate without one, especially when you talk mathematics. I'm going to make the lesson a little shorter, so I'm going to go through a number of examples here. But what I want you to do at the end of the day, after we finish the lesson, when you go home, so please make sure that you look again at this lesson, and you stop the recording after so in a minute or so I'll finish writing up a number of derivatives here. Stop the recording there, and then solve those problems by reading the antiderivatives yourself, right to left. So you make sure that you understand the concept of antiderivative. So over here, folks. So we have, you know what, let's start with x to the 10. X to the 10 prime is 10x to the 9, right? So then we have x to the, let's put something else, x to the 9 prime is 9x to the 8. And then x to the 8 prime is 8x to the 7, and so on, right? So we go down like this, dot, 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 we put dot, dot, dot. Let's say x cubed, right? So we go down to x cubed. X cubed prime is 3x squared. X squared prime is 2x. X primed is 1. 1 primed is 0, 0 primed is 0, right? So let's continue. We went down in decreasing orders of the powers. These are x to the 10, x to the 9, x to the 8, da, 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 going down, x cubed, x squared, x to the first, and x to the 0, which is 1. And then we can do, so naturally would be x to the negative 1, which primed is negative x to the negative 2, x to the negative 2 primed, which turns out to be negative 2x to the negative 3, folks. Make sure that you understand that, because it's going to be an exam question testing that thing, folks. So you want to make sure you know that. Then x to the negative 3 primed equals negative 3x to the negative 4, and so on. Well, our goal is to write all of these as antiderivatives, and we're going to write in words. And I think this is a good pedagogical approach on this part of a book. So this book has good parts, also some not so good parts, but this is one of the good things, that they make you write these in words so you understand the concept that way, and then they teach the formula. There's a symbol for antiderivatives, which we'll learn later. So over here, we're going to say the derivative. Oops, sorry about that. A bunch of things came up here. The derivative of, oh, not the derivative. See, I made a mistake. So the derivative is true. Well, that would have been true. The derivative of x to the 10 is 10x to the 9. The antiderivative, so we write this with antiderivatives. The antiderivative of x to the 10 x to the 9 is x to the 10. And then you write the next one, the antiderivative of 9x to the 8 is x to the 9. The antiderivative of 8x to the 7, yeah, the one that I have here, is x to the 8, the antiderivative of 3x squared is x cubed. And over here, so I'm going to write antiderivatives next to each of these things. The antiderivative of 2x is x squared. The antiderivative of 1 is x, yeah, because x prime is 1. The antiderivative, finally, there are 3 more here. The antiderivative of 0 is 1. The antiderivative of negative x to the negative 2 is x to the negative 1. The antiderivative of negative 2x to the negative 3 is x to the negative 2. And finally, the last one, folks, the antiderivative of negative 3x to the negative 4 is x to the negative 3. So here's what we notice, folks. I wrote all of these antiderivatives, and really this would be the exercise I would have asked you to do if we were in a more favorable situation here. So write these as antiderivatives. Make sure you don't get these wrong, because that's very important to understand that what you have on the right side, the antiderivative, is what you have on the left side. Okay. Now, this being said, folks, what can you, if you look here carefully, what can you see? So look at the powers here, 10, 9, 8, So all of these are continuous, right? So, I mean, the one going down by 1 all the way to x to the 0, right? So x cubed, x squared, x to the 1, x to the 0, then x to the negative 1, x to the negative 2, and so on. So the antiderivative of something is this, when you do the derivatives, you do really decreasing powers of x. Now, what happens with the antiderivatives? So the antiderivatives that I'm looking at are the antiderivatives of, we're going to learn how to ignore these constants 10, 9, 8, and such that are in front of these powers of x. So I'm looking at the antiderivative of essentially x to the 9th, x to the 8th, x to the 7th, x squared, and going down. X squared, uniformly, linearly x squared, x1, 0. So look here, interesting. So over here we say the antiderivative of x squared, the antiderivative of x, essentially, so we'll take care of a constant tomorrow, the antiderivative of x to the 0, and then the antiderivative of 0, and then the antiderivative of x to the negative 2. So it seems like there's a break here somewhere where x to the negative 1, we don't talk about the antiderivative of that, for reasons that will become obvious when we move on to calculus 2. So in calculus 2, you will learn what that is. But the point is that even though so now if we look on the left side here, even though these are decreasing powers of x, on the right side there is a break over here. So right here between zero, there's a skip between zero and x to the negative 2. And that can be explained with a logarithmic function. So that's one thing that you want to notice. The other thing that you want to notice, and this is going to be the last thing that I'll do today. So this is going to be in a way a shorter lesson because we introduced this concept and I want you to get familiar with the concept of antiderivative before we do any sort of calculations. Because what happens often, folks, is that people are not patient, so they want to see formulas and then they forget the meaning of the antiderivative, and that's problematic. So what I'll point out here is another thing that's kind of well, it should give you some food for thought. The antiderivative of 1, we said, is x. But you know what? What that really means that x prime is 1. But is x the only thing whose derivative is equal to 1? For example, wouldn't x plus 3 primed also be 1? It would, yeah, it is 1. Wouldn't x plus 7 primed also be 1? Wouldn't x minus 5 primed also be 1? All of these would be answer for the question, give me an antiderivative of 1. So this is a concept that has multiple answers. So again, there is not just one antiderivative, even though we said so on the previous page, there's multiple antiderivatives. But the thing is, and we could argue quickly that all these antiderivatives are just translates of each other. In other words, every single antiderivative is obtained from the other ones by adding up some constants. So if you take the antiderivative and you add various constants, you get another antiderivative of the same thing. All right, so this is food for thought for you for tomorrow, folks. Please consider looking at these antiderivatives again, the examples that I wrote there. Tomorrow, we are going to give some nice formulas and some rules for working with these antiderivatives. All right. One more thing, and I will be done here. So, of course, we did these powers of x, but why not trig functions? Why should we stay away from that? There's no reason to, right? So we can say, and here's one example. When you do sine x primed, you get cosine x, right? Well, so the thing is, folks. Oops, sorry about that. The thing is, folks, you can write this with antiderivatives, like we wrote the powers as the antiderivative of cosine x is, and we're going to say sine x. There we go. So this is the way to write the derivatives of sine and cosine with antiderivatives. Tomorrow we're going to mention secant squared and tangent, but for the time being, I think this is good enough. So we just started lesson again 3.9. I don't want to push too hard. Again, this is where you need to get. So this is your first time when you see these things, and you need to keep your toes in the water before you start swimming. So this is the role of this lesson, to kind of get you accustomed with the temperature of the water and all that before you start swimming. Tomorrow we're going to start swimming seriously. We're going to have some formulas, and we'll finish up this section. And then we won't talk about antiderivatives for quite a while until we get to the calculations of integrals with the fundamental theorem of calculus. So this is it for today, folks. I don't have any more stuff to. I don't want to cover any more stuff here. So if you have any questions, do let me know. I'm gonna stop the recording. I had a lot of trouble